Hello. Yeah, in the last class, we discussed about the work done and definitions of work and work done due to the frictional force and work done due to gravity and work done due to the applied force. Okay, today we are going to discuss about the applications of work done. See, in the first application, here we are having the first application. It is that, okay, first application we are having a body of mass m is lifted from the ground to a height h by using a minimum force. Okay, by applying a minimum force, I am lifting the okay object to a height h. Initially, it is on the ground. Okay, by applying a minimum force, it is raised to a height h. This is the height h from the ground. Now I want to find what is the work. What is the work done? Force applied. Okay, it is vertically upwards. Due to that, displacement is also upward. So, minimum work done by lifting force. Here we are calculating work done due to the lifting force. That's why we can say that the direction of force and displacement are along the same direction. So, according to our formula, F bar dot R bar, here displacement is H. So the direction of displacement and force are in the same direction. So it is Fr cos 0. So that's why we'll get it as F into H. Okay. Whatever the force it is there, that is equal and opposite to mg. So W equal to mgh. That is the work done due to the applied force. Similarly, work done by the gravitational force. Gravitational force is acting downwards, displacement is acting in the vertical upwards. So here the direction of force and displacement are along the opposite direction. So in this case, I can write as FH cos 180. Since it is opposite direction, theta is 180 degrees. In the same direction means theta equal to 0 degrees. So work done will be negative. Work done will be negative. Okay, fine. Okay, fine. Next step. Okay, next second application. It is that one end of a string is fixed to support and a body of mass m is attached to the other end of the string. If the point of support moves with acceleration a in the upward direction, work done by tension in the string when the body moves upwards. When the body moves upwards. See, here we are having that one end of the string is fixed to a fixed support. This is the fixed support. One end of the string is fixed. Okay. And a body of mass m is attached to the another end. Here we are having a body of mass m is attached to the other end of the string. If the point of support moves with an acceleration, okay, point of support moves an acceleration in the upward direction. Okay, okay. Work done by tension in the string when the body moves upwards. Okay, if we draw the free body diagram, okay, free body diagram from the center of the object vertically downwards, we are having mg. Towards the point of suspension, we are having the tension T. And see here, we need to find work done by tension in the string. Tension is acting in the upward direction and acceleration we are having in the upward direction. Okay. So tension, whenever the body is moving in upward direction, we can write tension equal to mass into net acceleration. Whenever it is moving upward, net acceleration, I can write as A plus G. And the displacement, it is the H. Okay, from here to here, it is the H. So work done is equal to work done by the tension is M into G plus A into H. Okay. The same thing, work done due to gravitational force. Okay. Okay. That is minus. Suppose if the body moves downward with an acceleration A, work done by tension. Whenever it is moving downwards, okay, then what will happen? Net acceleration, I can write as G minus A. Okay, so height will be downwards. Okay, that is displacement is downwards and tension is acting upwards. In this case, I can say angle between force and displacement is 180 degrees because direction of the force and the direction of the displacement both are in the opposite direction. Both are in the opposite direction. Okay, right? Okay, fine. Now, that is the second application. See, work done is negative as force and displacement are opposite to each other. Okay, is it clear? Okay, fine. Okay, next application. Next application it is that is a body of mass m is placed on a frictionless horizontal surface, that is smooth surface. A force F acts on the body parallel to the surface such that it moves with an acceleration A. Work done by the force acting on the body when the displacement is S. See, we are having an horizontal surface and it is a frictionless. We are having an object of mass. When a force F acts on the object that is parallel to the surface such that it moves, whenever a force is acted on an object, we will have a displacement. Correspondingly, we are having an acceleration. So work done, I can write as force times displacement. Here, the direction of the force and the direction of displacement, both are in the same direction. So I can write as Fs cos 0. F means, according to Newton's second law, I can write as Ma. So work done equal to MAS, right? If the same body moves with uniform velocity, it means that acceleration is zero. So work done will be zero, right? Uniform velocity means that, okay, uniform velocity, it means that velocity will be constant. It means that velocity is equal to constant. So when velocity is constant, acceleration is zero. Okay. Next, if the frictional force is considered, that means we are considering this as a rough surface having a coefficient of friction as mu. Then work done by the force to move the body with uniform velocity. Okay, that is whenever we apply a force, there will be a frictional force which will act on the object or on the body. On the body. See, then force required to move the body with uniform velocity. That is work done is equal to mu k Fk into S. That is mu k mg. Because frictional force Fk means mu k times n. On a horizontal surface, normal force is balanced by mg. So kinetic friction, kinetic frictional force, I can write as mu k mgs. That's why they wrote this. Okay, fine. Okay. Next, fourth case, it is that in the above case, if the body moves with uniform acceleration, work done by the force. That means we are having the frictional force and MA and MA. Okay. Okay. So the total force will be, we can write as F minus F is equal to MA. Okay, whenever the body is having an acceleration on a rough horizontal surface. So applied force, I can write it as frictional force plus Ma. Instead of force, they wrote it as F plus Ma into S. That is nothing but work done is equal to mu k mg plus Ma times displacement. Okay, this applied force F is equal to, okay, mu K mg plus ma. This direction of applied force and direction of displacement are along the same direction, or along the same direction. Okay, okay, fine. Next, application 3.4. A body of mass m and density d1 lies in a non-viscous liquid of density. Now, firstly, we'll see the what is meant by viscous liquid. Okay, viscous liquid. Suppose I will consider the two substances. One is water and another one is gum. And another one it is gum. Okay, water. Okay, if I touch the water, okay, there will be no opposing force will be there. But if we touch the gum, what will happens? Okay, there will be some opposing force will be there. Opposing force will be there. Due to that, what will happens? Okay, due to that, what will happens? The liquid or gum will have some what we call jerk nature. Will have a jerk nature. That kind of liquid can be called viscous liquid. Non-viscous means like water. Non-viscous liquid means like water. Here we are going to discuss on the, okay, non-viscous liquid, which is having a density d2. Now, what is the minimum work done to lift the body with uniform velocity through a height h in the liquid? Okay, here we are having a non-viscous liquid. We are having a non-viscous liquid. Okay, initially we are having a mass m. Okay, from the center of the object vertically downwards, we are having the weight. This is the weight. Okay, towards upwards, we are having the tension T. It is rising to a height. Rising to a height. So, according to the buoyancy, law of buoyancy, okay, that is upthrust is equal to loss in weight. Loss in weight. That is weight of object in air minus weight of object in medium. In medium. Weight of object in air means mg minus weight of object in medium means mg times density of the object in medium by density of the object in air. Okay, so work done is equal to mg times density of the medium, it is d2. Density of the object in air is d1 into h. Because this mg, you can see here, upthrust it is acting in the upward direction. Displacement is also acting in the upward direction. So work done is equal to mgh times 1 minus d2 by d1. Okay, 1 minus d2 by okay. So in this case, it is whenever the object is immersed in a liquid of density d2, object is having a density d1 and a liquid is having a density d2. So we can say that, okay, object means it will be in the solid shape. Liquid. Okay, so Obviously, density for the solid is greater than density for the liquid. So D1 will be greater than D2. So D2 by D1 will always be less than 1. That is density of the liquid by density of the object. By density of the object will always be less than 1. Will always be less than 1. This one. Okay. Wrote. Okay. Next application. Next application. Fifth application. A bucket full of water of total mass m is lifted up with uniform velocity using a uniform rope of mass m and length L. Okay. So now you see here, a man is pulling this bucket. Bucket is having a mass capital M. Now I want to find what is the work done by lifting the lifting the force in lifting the bucket full of water by means of rope. This rope length it is L. They gave, see, this rope length it is L. Whenever the man is lifting the bucket with the help of rope, then we can say that force it is upward direction. Force it is upward direction. The rope length it is L. Rope length it is L. So I can say that, okay, see, a bucket full of water of total mass, okay, and rope is having a mass, see, small m. So mg, okay. For the rope, if I pull up to the center, that is, it is a length L by 2, the remaining L by 2 will also come. So that is small mg L by 2. Or afterwards, you will study a chapter called center of mass. For a rope, the center of mass will lies at the center. Center of mass means, okay, the position at which all the particles in the given object are concentrated. Okay, say for example, in my pen, okay, what will happen it is, I can concentrate this pen or I can balance the pen at the center, right? See, some people, what they will do it is, they will rotate the basketball or football or volleyball at the tip of the finger. That means they are concentrating the total mass of the ball at the tip of the finger. At the tip of the finger. So that is the point at which the total mass is concentrated. That can be called as center of mass. Okay. Okay. So here work done by lifting the force in lifting bucket of full of water. That is work done of the rope by the person plus work done of the bucket. For the bucket, I can say that it is MGL. Okay. For the bucket, it is MGL. And here it is, okay, for the rope is having a mass small m into G L by 2. If I apply the force up to the center of the rope, then, okay, it is easier to pull the bucket as well as the remaining half of the rope. That's what. Okay. Okay, fine. Next one. A pendulum of length L, a pendulum of length L carries a bob of mass M. The bob is pulled aside through an angle theta with lower vertical by a horizontal force. Now see the diagram. Okay, here we are having the diagram. That is, initially we are having a bob of mass M. This is mass M. Whenever I apply a force, this bob will move or will rises to a height. Initially, it is having a length. Whenever I apply the force, it is the length L. Okay. Now, I want to find how much height it is raised, this H. In order to find, okay, here we are having a triangle C, A, B, C. In this triangle ABC, AC is equal to L. At B, it is right angle, that is AC will be hypotenuse. So I can write it as AB as L cos theta. Okay. And this point I am considering as D. So AD, I can write it as AB plus BD.
168.
AB plus BD. Okay. Okay. AD, this is the total L. And AB, it is L cos theta plus H. BD, see this length. Same distance now. Okay. So H is equal to L into 1 minus cos theta. That's why the work done is equal to, okay, F bar dot R bar. F bar dot R bar. So that is what we'll get. Force, it is acting vertically downwards. Okay. And the displacement, see, in the upward direction, this is the displacement H. Both are in opposite direction. So I can write as minus F into R. So work done is equal to minus mgh. That is nothing but minus mgl into 1 minus cos theta. That is. Now work done by horizontal force. By applying horizontal force here, the bob is moved. Even okay, apply force.
అయితే దాని స్విగ్గీలో తీసుకున్నా సార్ వదిలేసాను.
అది
జొమాటో
ఇందాక వచ్చింది ఇది 929066.
Lari komali mulai
Okay, వచ్చింది. Okay, H is equal to L into 1 minus cos theta. Due to the applied force, we can say that it is horizontal. We are applying horizontal like this. And here we are having that it is theta. This is theta. And this is the horizontal. Okay. Okay, fine. Here it is theta means 90. And this one it is 90 minus theta. Okay. Okay, fine. Now, if I draw a perpendicular here, here it is 90 minus theta. That means this is theta. Okay. And here it is perpendicular. So this value, base value, it is F, horizontal force. So this one, we can say that it is F sin theta. Okay. So it is, instead of force, we are having F sin theta, and the displacement, it is length L. Okay. Force and displacement are along the same direction. So work done will be FL sin theta. FL sin theta. Okay. Okay, fine. Next one. A uniform rod of mass M and length L is suspended vertically if it is pulled aside through an angle. Okay. Through an angle theta to the lower vertical. Okay. It is same as, okay. It is suspended vertically if it is pulled aside through an angle. work done by gravitational force. Okay, gravitational force will act from the center of the object. Here also we are having that. Okay, this is the height h. Okay, from center. So length will be at the center. So that's why we are writing it as minus mg L by 2 into 1 minus cos theta into 1 minus cos theta. Okay. Uh, Harshita,
ఎస్
Srikar,
సార్.
ఏ అందరు జాయిన్ అయ్యారా?
లేదు సార్.
మీరు అది ఐపీ చదువుతూ ఉండండి. నేను రికార్డ్ చేసి మీకు లింక్ పెడతాను.
ఓకే సార్.
అందరూ లీవ్ అయ్యి మీరు ఐపీ చదువుకుంటూ ఉండండి. ఈలోపు మీకు నేను లింక్ పెడతాను. ఓకే,
ఎప్పుడు స్టార్ట్ చేశారు సార్?
1:15.
ఓకే.
Okay, next, a ladder of mass m and length L. మీరు హర్షిత, మనీష్,
ఎస్ సార్.
కాలేజీకి రండి మీరు. 125 మనీష్.
ఓకే సార్. యాక్చువల్లీ 2 o'clock క్లాస్ ఉంది కదా అని.
అవును, లేదు రండి మీరు కాలేజీకి రండి, ఎగ్జామ్ రాయండి. మనీష్, హన్విత్
సార్
ఐపీ చదవండి. కిరణ్,
ఎప్పుడు సార్ ఎగ్జామ్?
నువ్వు కాలేజ్కి వస్తే
Exam?
పెడతాను.
సార్ నాకు
కాలేజ్ రాకపోతే నేను పెట్టను.
మొత్తం జలుబు ఉంది సార్, నాకు బాగా కోల్డ్ కాఫ్ ఉంది, నేను రావట్లే, అందుకే పొద్దున్న రాలేదు సార్.
ఎగ్జామ్ అయితే నీకు ఉండదు, ఎగ్జామ్ అయితే నీకు ఉండదు.
రేపు వచ్చి రాయొచ్చా సార్? రేపు వచ్చి 2 రాస్తాం.
ఎవరు? Okay, see the next application, that is 8th application. A ladder of mass, okay, a ladder of mass m and length L resting on a level floor, okay, on a level floor is lifted, okay, is lifted and held against the wall. Here we are having a ladder, okay, it is having a support from horizontal surface and vertical surface. This ladder is making an angle theta with respect to horizontal. They are asking to find what is the work done by gravitational force. Whenever they are asking gravitational force, that is the force is acting from the center of object to the vertically downwards, to the vertically downwards. So due to the gravitational force, I can write as force is acting downwards and displacement is upwards. So that is minus mgh. When force is acting downwards and displacement is upwards, then the angle between them will be 180 degrees. So work done is equal to Fr cos 180. Cos 180. Cos 180 means minus 1. So work done equal to minus Fr. That is, since we know that here h, in this triangle you can see, okay, in this triangle hypotenuse is L by 2. Opposite side is h. So I am considering sine theta. Sine theta equal to h by L by 2. So h is equal to L by 2 sine theta. Okay, that is this one. So work done is equal to minus mg L by 2 sine theta. Okay. Okay. Next. In the next application, that is ninth application, you can see a uniform chain of mass m and length L is suspended vertically. The lower end of the chain is lifted up to the point of suspension. Okay. Okay. The lower end of the chain, this one. Okay. Suppose let us consider this is the total length of the chain. Okay. The lower end of the chain they are asking. Okay. So here it is that lower end means suppose from here to here it is L by 2 and this one it is L by 2. Okay. That means lambda, that is linear density, it is constant everywhere. It is the constant everywhere. So here we are having that it is, let us consider this is A, this is B, and this point is C, such that length of AB is equal to length of BC, that is L by 2. So M by L equal to mass of AB by length of AB. So mass of AB is equal to M by L into length of AB. Okay. So we'll get it as M by 2 because length of AB means L by 2. So mass of AB equal to M by 2. So work done in pulling the chain, we can write it as I am pulling the chain. Okay. Okay. Display upwards and mg is acting downwards. So m by 2 into g, displacement L by 2. Since both force and displacement are in opposite direction, angle between them it is 180. So minus mgl by 4. That is. Okay. Na? Okay. Like this, we are having the applications. Okay. Okay. We'll see the next application. Next application, it is 10th application. A uniform chain of mass m and length L rests on a table having 1 by nth part. Okay. Already in the classes, we discussed this chain. You can see once, please go through it. Okay. On the inclined plane also we discussed it. Okay. This one on the rough inclined plane, smooth inclined plane. Okay. And this one it is with respect to thermodynamics. Work done in compressing a gas in a cylinder by a piston. Okay. Work done is force times displacement. Force I can write it as pressure into area times displacement dy. That is nothing but dv. So work done equal to PV, P times dv. And here we are having the examples of calculating the work done. Okay, of calculating the work done. You can see here. Okay, like this. Okay, today once apart from your this weekend syllabus, okay, once please go through these applications of work done, of work